so page 152, second half of section 2.2, we were looking yesterday at graphing those polynomial functions that have a higher degree. And so yesterday we had noted that in a typical situation, like let's say you have a polynomial that has a degree of 4, it should have 3 terms. But we saw yesterday that that's not always the case. Like one of the examples that we did was a quintic. It was a degree of 5. It should have had 4 terms. And instead, when we looked at the graph of it on our calculator or in our textbook, it really looked more like a cubic, like it only had 2 terms in it. And so we talked about the fact that what causes those turns in your graph is that your every solution is an x-intercept. So if I have something that has a degree of 5, it should have 5 solutions if they're all real and they're all different. If it has 5 different real solutions, that graph is going to have to turn 4 times in order to hit those 5 x-intercepts. But if we have some of those solutions that are imaginary, I can't graph those as x-intercepts. Or if I have multiple solutions at the same point, like a double root or a triple root, then my graph doesn't have to turn to go catch a root somewhere else. Okay, so what does it do when it hits a double root or a triple root? And so that's what we want to look at today. How do we handle those repeated zeros or that multiplicity? And so top of page 152, they give you both of those bold print terms. They say that if you get the same solution more than once, like one of the examples we had yesterday, we got x equals 2 4 times. That's 4 different solutions. That is a repeated zero. And it says if you get a repeated 0 3 times, then that means that it has a multiplicity of 3. So if you get x equals 2, x equals 2, x equals 2, you get that same answer 3 times. That's a repeated 0 with a multiplicity of 3. So those are those bold print terms that they're talking about on the top of page 152. All right, so let's look at an example. Just to kind of pick up where we left off yesterday, remember that we said that if you have a polynomial that has a positive leading coefficient, then the leading coefficient test tells you that that polynomial will stop going up. If it has a negative leading coefficient, then the leading coefficient test tells you that polynomial will stop going down. If it has an even degree, like 2 or 4 or 6, it's going to start and stop in the same direction. So once I figure out how it stops, then that would tell me how it starts. If it's odd, like 1 or 3 or 5, it's going to start and stop in opposite directions. So again, once I figure out how it stops, then that'll tell me how it starts. So when we start with f of x is equal to x times x plus 2 to the second, what's my leading coefficient? 1, right. So how is my polynomial going to stop? Up or down? It's going to stop up, right, because that was a positive 1. My leading coefficient test tells me that it will end going up. My end behavior, my stopping behavior, will be that it stops going up. What's the degree of this polynomial? Be careful. I have x to the second right here, but I have another x over here, right? So, right, it is a cube because if I put that back together, if I distributed that x, they were kind enough to take out the greatest common factor for me, but if I distributed that x back through, I FOILed this out and distributed that x back through, I'd end up with x to the third, right? So this is really a cubic. So if it stops going up, how's it going to start? Down, right? It's going to be opposite because it's odd. So I know that if it's typical, it should, if it's a degree of 3, have 2 turns. So it should start down, turn once, turn twice, and stop going up. That should be its typical shape. So let's see if this one is typical. So if we go through, we already had the greatest common factor of x taken out for us, so we could set that x equal to 0. Then let's take our other factor, x plus 2 squared, and let's set that equal to 0. That literally means x plus 2 times x plus 2, right? So if you solved one of those, you would get x equals negative 2. and I'm going to get that same answer twice. It's going to be a repeated 0 with a multiplicity of 2. We also call that a double root. If you get 3 of the same thing, we typically call it a triple root. 4 of the same thing, a quadruple root. You get the idea. So when I come over to graph this, I'm going to have a double root at -2, and I'm going to have a single root at 0. So I start following this path right here, and I say, okay, I start down, and I come up, and when I hit that double root, I'm actually going to turn on that double root. If you think about it, we've seen this before. One of those 6 graphs that we're supposed to know what it looks like from page 100 is a quadratic of a y equals x squared parabola. If you think about that, if you solved y equals x squared, you'd get a double root at 0, right? And what does that graph do at 0? It turns, right? The idea is kind of this. If I had a single root, it's like I would be coming up and going straight through that single root. But then I have a second root there, so I got to turn around and come back down through that same root. And so the way that we indicate that is that we turn on that root when I have a double root. And then I could turn around and come right back up through that single root at 0. That's what that graph looks like. So we know what a single root looks like. If you have one solution, x is equal to 2, your graph is going to go straight through at that single root. If you have a double root, like we talked about with y equals x squared, and like we just saw with that example, if you have a double root, it's like your graph is coming down through and has to turn and go back up through again for the second solution, so it will turn on the point if you have a double root. If you have a triple root, meaning that you have 3 solutions at that same point, it's kind of like your graph is coming up through for the first one, and then it has to turn and come back down through for the second one, and then it has to turn and go back up through for the third one. So we've mentioned that, you know, if you have a degree of 3, it starts and stops in opposite direction. We also know what y equals x cubed looks like. That's one of those 6 graphs from page 100. So if you think about it, for y equals x cubed, it has 3 roots at 0, and what does it do at 0? It does what we call a slide, where it doesn't go straight through, but it kind of has a little bit of a slide there in the center so that we can differentiate between a single root and a triple root. So if you have 3 solutions at the same point, you're going to slide through at that point, okay? So now that we know how to graph that, it'll help us when we have those repeated zeros. All right, example number 6 asks us to go the opposite way. They've been giving me the equation and asking me to come up with the solutions and the graph. For example number 6, they give me the solutions and ask me to come up with the equation. So for example 6, it says, find the polynomial function with the following zeros. X is equal to -2, x is equal to -1, x is equal to +1, and x is equal to +2. All right, so we basically want to work backwards up through a problem. For instance, if I have x is equal to -2, the step above that was, instead of writing it in its solution form, we wrote it in its factor form. To write it in its factor form, you basically just set it equal to 0, right? So if I have x is equal to -2 and I want to write that as a factor, I'm going to set it equal to 0. Some of you can just look at that and go, well, obviously that would be x plus 2. But if not, think about how would you set that equal to 0? You would just add 2 to both sides, right? So that'd be x plus 2 is equal to 0. Same idea for this guy. For x is equal to -1. If I want that set equal to 0, what am I going to have to do? Add 1 to both sides, right? So that would just be x plus 1. All right, how about x equals 1? What's its factor form? -1, right? And how about x equals 2? X minus 2, right? Okay, so now we've got it in its factor form. So if we go up to the next line, the next thing that we would typically do is have all of those factors strung together. Instead of each of them being equal to a separate 0, we would string them all together set equal to just 1 0, right? So let's do that. Let's string them all together, x plus 2, x plus 1, x minus 1, x minus 2. Let's string them all together and set them equal to 1 0. And then we're just going to need to multiply these back together again. Now, if I multiply these back together again, I could start at the left and just work my way straight across to the right. So I could go through and do x plus 2 times x plus 1, FOIL that out, I'll get a trinomial. Take that trinomial and multiply it times this binomial, get a new polynomial. Take that polynomial, multiply it times this binomial, get a new polynomial. I definitely could do that. But our theme is typically work smarter, not harder, right? So do you see anything that might be a shortcut to that process? Or that might make it easier?
Do x plus 2 and x minus 2.
Why would I want to do x plus 2 and x minus 2? You are exactly right. What happens when I multiply those? Do you get a trinomial when you multiply x plus 2, x minus 2? No. You get a binomial, right? That's the difference of squares, right? So if I went through and I did x plus 2 times x minus 2, I'd get a binomial instead of a trinomial. What else could I do?
X plus 1, x minus 1.
Exactly. X plus 1 times x minus 1. Now I have another binomial. Then it's just multiplying two binomials. That's foiling, right? That's so much easier than starting over here and working straight across like we were mentioning. Okay? So let's go that route. Absolutely fabulous suggestion. So let's go through and multiply x plus 1 times x minus 1. And again, that's our difference of squares, x squared minus 1. What if we multiply x plus 2 times x minus 2? What do we get? X squared minus 4, right? And so here, yeah, we do have to FOIL, but that's okay. That's a whole lot easier than the other alternative that we were talking about. So we could go through and we could say x squared times x squared is x to the 4th. X squared times negative 1 is negative x squared. Negative 4 times x squared is negative 4x squared. And negative 4 times negative 1 is positive 4. Any like terms? Yeah, the x squareds, right. So if I combine those, what would I get?
Negative 5x squared.
Negative 5x squared. Now, for these problems, even in this example, it says there are many correct solutions. In the back of the book, when you do a homework problem like this, it will probably say something like answers may vary or there are many correct solutions. The reason for that is, yes, this is the base polynomial, but there would be a whole family of functions that would give me those same solutions. Because if you think about it, if I went through and I multiplied this whole thing by a positive 2, I'd still get the same solutions, right? Or if I multiplied it by negative 15, or if I multiplied it by positive 2,376.5, I'd still get the same solutions. That's just a common factor. So there are literally an infinite number of possibilities here, but that is our base function that then, we could have a constant multiplier times. All right, look at example 7. Example number 7, they want us to kind of start putting together all the pieces that we've been talking about. For example number 7, it says sketch the graph of the polynomial function by hand, not doing this on our calculator. And we want to use all the tools that we have. We want to use the leading coefficient test to figure out how this is going to start and how it's going to end and how many turns that it's going to have. We want to solve it and find the zeros because our zeros or solutions will be our x-intercepts. And if we have multiplicity of roots, we'll know how to address that. And then we could just make an XY chart for anything that we still were unsure of what that portion of the graph looked like. If I were to make an XY chart for this graph right now to sketch the graph of that to come up with an accurate graph, I'd easily be plotting 10, 15 points. We're going to be able to graph a nearly perfect one with just 2 points once we use these other tools that we have. Okay? So to begin with, leading coefficient test, how's this going to end? Up. How do you know that? Positive 3, right. How's it going to start?
Correct.
Up. How do we know? Because this is a degree of 4, and that's even. So when it's even, they start and stop in the same direction. Odd, they start and stop in opposite directions. All right? How many turns would it typically have? It may not, because we may have some imaginaries or multiplicity, but typically It would have 3, right? So we know its basic shape. It would start up, it would turn 1, 2, 3 times and stop up. So it'd kind of be that W shape. All right, so now that we know what it looks like, let's figure out where it's going to go on that graph. So let's find our x-intercepts. So what's the first thing that we would do for this guy to solve it? All right, greatest common factor. So what could I take out? X cubed. So if we take out x cubed, we'll be left with 3x minus 4. All right, let's set each of those factors equal to 0. So we'll set x to the third equal to 0. That literally means x times x times x, right? If you wrote that out. So that would be x equals 0, x equals 0, x equals 0. I'm getting 0 as a solution 3 times. That's a repeated 0 with a multiplicity of 3. That is a triple root. All right, then we can set 3x minus 4 equal to 0, and that'll give us x equals 4/3. So I'm going to have a single root over here at 4/3, and I'm going to have a triple root over here at 0.
Is it plus r on
TR, triple root.
All right, so we're going to start up. So I know we're going to start up over here. What happens at a triple root? A slide, right? So I'm going to start up, and I'm going to slide through my triple root. And then what happens at a single root? I just go straight through it, right? So I know that I'm going to have to come straight up through so that I can end going up for that single root. And I know that it's going to follow this basic shape. So really all I don't know at this point is I don't know what my graph is doing over here. I don't know how steep to make this. Like, is it pretty flat or is it pretty steep? I don't know. And over here, I don't know how far down this is going. Like, is it kind of shallow or is it really deep? I'm not really sure what's going on there either. So I'm just going to plot a couple points to clear up that ambiguity. So I'm going to come over here and plug in a -1 to give me a clear picture of what the graph looks like over here. And I'm going to plug in a +1 to give me a clear picture of what's going on over here. So if we plug -1 into that function, we'll get 7. So yeah, that's really steep over there.
So you have one into the starting function?
Uh-huh. -1 into our original function there, because this is the graph of f of x. So we'll plug -1 into our original function. And then I'm also going to plug +1 into my function. And I get -1, so that lets me know this was pretty shallow down here. It doesn't scoop way down. So we have a nearly perfect graph with just 2 points. And again, we would have needed quite a few to get that kind of clarity otherwise. Additionally, look what we would have been plotting. This is -1 right here, right? The majority of the change in this graph comes between -1 and +1. That means we would have been plugging in about 8 fractions, right? So much fun. So utilizing those tools that we've learned definitely makes our life a lot simpler. All right, over on page 154, the last thing we want to look at is something called the intermediate value theorem. Page 154, intermediate value theorem. It says the intermediate value theorem concerns the existence of real zeros of polynomial functions. The theorem states that if a f of a and b f of b are 2 points on the graph of a polynomial function, such that f of a is not equal to f of b, then for any number d between f of a and f of b, there must be a number c between a and b such that f of c is equal to d. Really? All right, let's go back and interpret that. Here's the idea. It says if you have a point a f of a, okay, so here's a, and here's the y value that goes with it, f of a, so that point right there would be a f of a. And you have b f of b. So come over here. Here's a different x value of b, and the y value that goes along with it is f of b. So that point right there would be the ordered pair b f of b. Okay? So if you have those 2 points, there are 2 points on the graph of the function, and f of a doesn't equal f of b. That just means their two y values aren't equal to each other, so they're not forming a horizontal line. One is above the other one. Okay? So I have f of a up here, and I have f of b down here. Then it says for any number d that comes in between f of a and f of b, so that would be a y value in between these two y values, then there must be a number c in between a and b. There must be an x value in between these two x values, such that f of c is equal to d, such that if you put c into the function, it would give you that d value. Here's the short version of it. You cannot have a y without having an x, right? There's no way that you can have a y value up here without it having a corresponding x value down here. So what they're saying is if there's a y value in between these two y values, then it has to have a corresponding x value down here in between these two x values. That's the abbreviated version of the intermediate value theorem. What we want to use the intermediate value theorem for our intents and purposes is proving that there is a root between two values. So for our example, it says if f of x is equal to 3x to the fourth minus 4x to the third, that function we were just working with, is there a root between 1 and 2? Now I can come back up here and see, okay, here's x equals 1, here's x equals 2. Yes, there's a root in between there. I can see that. But if I didn't want to have to graph the whole thing and I was just checking to see, is there a root between those two values? Is there going to be an x-intercept there? Here's a fast, easy way that I could do that. I could go through and I could plug each of these x values in, 1 and 2. I'm going to plug 1 into the function, and I'm going to plug 2 into the function, and I'm going to see what I get. All right, so when I plug 1 into that function, 3 times 1 minus 4 times 1 gives me negative 1. And when I plug 2 into that function, 2 to the fourth times 3 minus 4 times 2 to the third is going to give me 16. So what I'm looking for is a sign change. I cannot go from a positive 16 to a negative 1 without going through 0, right? You can't switch from a positive y value to a negative y value without going through 0, right? Same thing would be true in the reverse. You can't go from a negative y value to a positive y value without going through 0. Why is that significant? Because when y is equal to 0, I have an x-intercept, right? So according to the intermediate value theorem, if I can show that there is a sign change here, then I know there had to have been a 0 in between those two y values, right? And if there is a 0, according to the intermediate value theorem, if there's a y value of 0 in between these two y values, then there would have to be an x value that goes along with it in between those two x values. And if my y value is 0, then that would be a root, an x-intercept. So that would be a way of proving that there was a root between those 2 points. So the bottom line is, when they say, is there a root between 1 and 2? The real question is there a sign change between 1 and 2? If there is a sign change between those two y values, then yes, there is a root between those two x values. If there is not a sign change between those two y values, then no, there's not a root between those two x values. Okay? All right, so here is our homework for tonight. And remember that we have our quiz this Friday over 2.1 and 2.2 using scientific calculators, but no graphing.